So we were kind of finishing up, and we'll kind of go from where we were yesterday. We were talking about kind of how atoms, and the different particles that atoms have in them. Kind of jump. So we have protons, we have electrons, we have neutrons. So we get kind of three different materials inside every atom that makes them have different properties. And really the what makes elements different. So what makes something a hydrogen versus something an oxygen versus a carbon, that's related to the number of protons right here. So having a certain number of protons is actually what controls what element you have, what element you are. And then the other elements, aspects of the element, are the fact that protons have a charge. So you don't want too many positives altogether. So you got to start bringing in some negatively charged items to kind of make up for those positives, to kind of adjust the level of constant of charge on there. So we have kind of these electrons that are coming in, changing the charges of those elements, kind of bringing them closer to zero. So we don't want a lot of pluses. Carbon would be +6 if we didn't have any electrons. But if we can bring in some electrons, we can get it out to about a zero charge, which is better for that kind of setup there. So we have electrons, we have protons, and we can figure out the charge of an atom. What charge, how many extra electrons or how many fewer electrons it has, as long as we know how many protons there are. And if we either know how many electrons there are, or if they give us the charge, then we could figure out how many electrons there are. So that's what we were looking at here. This is kind of, in general, they're the same. So if you had 82 protons like this lead atom over here, if they don't say any otherwise, they don't say there's any extra electrons, then there's probably 82 as well, because the pluses and the minuses are going to cancel each other out. But we do have, skip this. But we also have things that are ions. We have things that are ions, and that's when we do have different numbers of electrons. So we can have things like these neon atoms. So neon is an atom, neon's an element, but neon also can form ions, maybe with negative charge, which means that it has an extra electron or one more electron than a normal zero charge on neon would have. So depending on if you have more electrons, you're going to be negative. So like this one has an extra electron. It has a -1 charge. This one also does. This one has one more electron than an uncharged atom. This one's got 2 extra electrons. It's got 2 extra electrons, and that means that it has a -2 charge, because normally oxygen, if we look on a periodic table, there's one over here. O right here is in that top corner. O has 8 protons normally. So oxygen normally has 8 protons. But if you went and gave oxygen 10 electrons, so number of protons minus the number of electrons, and we'll say it has 10 electrons, then we get 8 minus 10, we get overall -2. And that's the charge of this particular oxygen here. This oxygen has 2 more electrons than an uncharged oxygen was, and that means it has a -2 charge. The sodiums, or the chlorine here, has 1 extra electron. It has, normally chlorine would have, chlorine up there would normally have 17 protons. But if it had 18 electrons, then we could subtract 17 from 18. We get a -1. So that chlorine there has 1 extra electron than a normal chlorine would, so it has a -1 charge. So as long as we know how many protons there are, and that's what we can get from our periodic table. So we would look on a table and you'd see what number it is. So that's kind of that big number. If you were looking at an atom's name or atom spot on the periodic table, you'd see the symbol for it. And there's usually a number right on top there. That's the number of protons. And then there's a number down here, and that's a mass. And we'll get to the mass in a little bit. That's basically the protons plus the neutron number. So if you wanted to know how many protons and neutrons, that's down here, number of protons on top. So if we know how many protons there are, like these oxygens here, and we knew how many electrons, we could figure out if there's any more or any less for those. And you can either have more electrons or fewer electrons, right? This sodium has 11 minus 10, so that's a +1 in terms of charge, versus the sulfur, 16 minus 18, 16 minus 18 is -2, or 79 minus 75, that's +4. So we can kind of get either pluses or minus charges. You can have plus or minus charges. And just like on this table here, you can see like the charge is something like V. The number of protons for a V would be 23, or the number of protons for a lithium would be 3. It's just that number on top right there. So if we wanted the number of electrons or protons in lithium, we would look at that number right there. So the proton number is right on top. It's pretty important. So it's kind of the first number you see for these elements there. So those were the two particles we talked about yesterday. And we were kind of wrapping up with talking about neutrons, which are this third particle, but they don't have a charge, right? Electrons are negative, protons are positive. So we get something that's +1 charge, we get something that's -1 charge. So this is plus versus minus. Neutrons don't have a charge, so they're not plus, they're not minus, they're nothing, they're neutral. And the other thing that these have going on is that they all weigh different amounts, right? Because these are all matter. Matter has a mass. So matter has a mass, and the mass of a proton is pretty standard. It's just 1. So if you had 1 proton, it would have a mass of 1. If you had 100 protons, it would have a mass of 100. Electrons have a mass, but it's so small that we kind of ignore it. And then protons also have a mass, and they have a mass of 1 as well. So both protons and neutrons have the same mass. They have a mass that's equal to 1. So two different elements with a mass of 1, or two different molecules with a mass of 1. But what the neutrons are doing is the neutrons are hanging out in this nucleus over here, and they're helping keep everything stable. So you have the electrons out here in blue, and the protons and the neutrons in the nucleus right here. And the neutrons are kind of holding the atom together. They're giving some space between the protons. They're kind of helping the protons hang out together. And it's kind of like with when you're looking at an atom, right, you have atoms that have protons in the nucleus, and all those protons are pluses. And if you have too many pluses together, they start to not get along very well. They start to push against each other, just like if you take two magnets and you try to put them together, they try to push each other apart. Magnets don't do so well near each other when they have the same charge, and pluses are the same way. Lots of pluses together don't like being together all the time. And just like if you have siblings and you've ridden on a long car ride and you're all crammed together in the back seat, you start pushing each other and not getting along. Sometimes your parents say, don't make me come back there and separate you two. And that's what the neutrons do. The neutrons are there between the protons to kind of buffer them from hitting each other. So you got your protons here with the neutrons in the middle. So you got the neutron there, kind of keeping everything separated, making the nucleus just a little more stable. Yeah. They start off the same number and then they get more neutrons. So like for low atoms, and you don't need to know it because we can always figure it out. But like for low atoms, they're about the same. So like carbon has like 6 and 6. But then when you get to bigger atoms, it starts to be like almost double. So it'd be like 16 and 32. So as the new elements get really, really big, they need even more neutrons to help keep them separated out. And then if you go to something like a uranium, it's like 90 and like 200. So they kind of, there's usually more neutrons than protons, or about the same. So if you ever see more protons than neutrons, you probably got something wrong with that atom. And that's usually what makes an atom radioactive. If there's not enough neutrons, the atom actually gets so unstable it starts breaking up, and it gives off particles that aren't so good for us. So that's what we'll talk about a little bit later too. So this is for the atoms here, the neutron number. So if we wanted to know how many protons or neutrons are in an atom, that's a pretty important number because it does control how stable that atom. Like right now, these are stable atoms with about the same number of protons and neutrons here. So same number here or more as we get larger atoms. And that makes these atoms stable, and they stabilize the nucleus. But if we wanted to know how many neutrons are in this atom, we could count it. But rather than saying that this atom has 3 protons and 3 neutrons, since we're already writing down the number of protons as an atomic number, they'll just report the combined number of protons and neutrons as the mass of the atoms. So atoms have a mass of 1, neutrons have a mass of 1, and protons have a mass of 1. So what they usually do is they just count the total number of protons and neutrons and report that number together as a total mass. So you know that every time you see a mercury, it has a proton number of 80 because that's its atomic number. And then mercuries may have 200 total particles, but you know that 80 of them are protons. And then you know there's some number of neutrons that's going to sum to 200. So then that means there's 120 there. So like a mercury atom would have 120 neutrons, 80 protons, and then the total mass is then 200 because there's 200 things total in that nucleus. And there's also some electrons there. But again, the electrons are so small in terms of mass that they usually just ignore them. They just kind of say, all right, well, we know there's electrons, but you'd have to have over 1,000 electrons before this mass gets even goes up by half a unit. So we're going to ignore the electron number in terms of the mass of everything because it's so small. So you could look at these in terms of grams, but it's a really small number. So we use AMU all the time because grams are so small. No one wants to write this out for the mass of a proton. Or if you had, if you had 100 of these, we'll get rid of 1 0 or 2. But we don't need to use numbers that tiny. So rather than using really tiny numbers, we're going to be using the mass of an atom in AMUs instead. So rather than saying it's 10 to the minus 22nd grams for a nucleus mass, we'll be using these AMU numbers instead. So that's why we use AMUs, is because the mass is so small for these electrons and protons and neutrons that it's not worth writing out all those zeros there. It'd be a very small number, lots of zeros to write. Oops, let's skip that one. Just jump to there. So if we wanted to figure out like the mass of an atom, what we could do is, as long as we knew what atom we're working with, and they'd either have to tell you the number of electrons and neutrons, or maybe it's something that we can calculate based on other information. But as long as we know the number of protons, number of neutrons, and the number of electrons, then we can actually figure out lots of stuff. We could figure out the mass of this atom. We could figure out the charge of the atom. So the mass is just the number of protons plus the number of neutrons. And then the charge is the number of protons minus the number of electrons. So if we know numbers of protons and then these other two things, we can figure out lots of different materials about an atom, kind of in terms of its charge or in terms of its mass. Again, usually mass atoms have no charge, but sometimes they do, and that's when they become the ions there. So for this atom here, this helium atom, we could get told what it is, and they tell you all this stuff. They might not tell you the proton number. In that case, you'd have to look it up, but that's always going to be the same. Every helium atom we'll ever see is going to have a mass of 2, atomic number of 2, and that's just, we would go to our little periodic table here, and we would see, He, and there'd be a 2 up there. And that tells us that we've got an atomic number of 2 for this particular atom here. So if we wanted to figure out what the mass of a helium is, we'd take our number of protons and our number of neutrons, and we would add those together. So for the mass of this helium here, 2 protons plus 2 neutrons gives us a mass of 4. So we know the atomic number, which is just from the periodic table. It's also the number of protons. We know the mass, which is the number of protons and neutrons. And if we wanted to know the charge as well, we could also figure that out. Charge in this case is 2 minus 2. So it's got a charge of 0. So you could write this as kind of He, and you could either put a little 0 there, or you could just write it as He without. So that would be another way of kind of writing helium for this case here, no charge. We know the mass is 4. We know the number of protons is 2 for every helium there. Do something similar for like the sodium here, right? Sodium, if we wanted to know the mass of that, now there's a little bit more neutrons. So this is starting to get a little bigger. So as atoms get bigger, the number of neutrons compared to protons goes up a little bit higher. So rather than having one of each, you get one and then a few extras. And the sodium here has 11 protons, 12 neutrons. It's got a total mass of about 23. And then we know the atomic number again because the number of protons is the atomic number. So atomic number is always going to be the number of protons, and that'll be that number. Again, if we were looking at a periodic table, it would be right on top there, and then a name of the atom right after. And we can do that kind of for a couple different atoms. And you can see as the atoms get a little bigger, the number of neutrons compared to protons goes up just a little bit. So copper's got 29 protons, but it's got 34 neutrons, so a few more, just like the gold, the sodium had 1 extra neutron compared. This one's got about 5. Now we get about 10 more. But no matter what the number of protons and neutrons is, you can always figure out the mass by just adding them together. 79 plus 91 comes out to 80, 170 mass units. Again, these are all neutral because they have the same number of electrons and protons, so that charge is 0 there for those. But we can figure out kind of the mass of an atom by kind of adding those up. And we're going to be using AMUs because, again, we don't want to have to use grams. It would be such a small number of grams that we use AMUs instead for these. So AMU is just atomic mass unit. So, right, atoms are what we're weighing. So the mass of an atom is a atomic mass unit. Very simple name for that. Very straightforward name. And then the reason we need to calculate these masses is that this particular gold atom here has a mass of 170. But there may be other golds that have only 90 neutrons, or there may be other golds with 92 neutrons. So the mass of this gold can actually change a little bit depending on what particular gold atom you have. So that's why we want to be able to kind of know what the mass of an atom is, because different golds might have different masses. If gold loses a neutron or gains a neutron, its mass could go up or down, but it's still gold because it's still got that 79 protons. As long as you have 79 protons, you're gold. The mass doesn't matter as much. It just makes the gold a little bit more or less stable, which could make it radioactive, which is what we'll talk about later today as well. And then, like we were talking about before, when we're thinking about atoms, we always kind of draw them as these little spheres here. And this blue part of the sphere, this is where all the electrons hang out. And then most of the mass is in the middle of the atoms. So atoms have a lot of mass, but it's all in one spot. So they're actually relatively densely mass, and then they're really, really light everywhere else. So it's kind of a interesting way that atoms are arranged is there's not much mass at all in this area over here. So there's lots of area with low mass and just electrons. And then there's one area that has really, really high mass in the center there for those. So that changes some of the kind of properties of the way atoms behave. They have to kind of collide just right for chemical reactions to occur. And when we want to talk about mass, or when we want to talk about proton numbers, when we talk about the masses and everything, we can kind of use a little way of kind of writing these out a little bit simply. So rather than writing something like this, right, sodium with 11 protons, 12 neutrons, electrons, there's a kind of shorthand way of kind of writing all those symbols. And what they'll do is they'll write kind of the name of the atom. So if you had like a gold atom, for instance, and you wanted to know, what they'll do is they'll put the mass of that gold up here. So if you had a gold that weighed 200 AMUs, that means there's 200 neutrons and protons. They'll put that 200 up in the corner, and then they'll put the other atomic number down here, which I think is 79. So they'll put both the atomic number down in the lower left corner, and then the mass number in the upper corner. And that's just the same as saying that this is a gold with 79 protons, and it's got 121 neutrons. So they could say that this is a gold atom with 121 neutrons, 79 protons. But what they do instead is they use this kind of short notation here. So they have, right, the mass of this, 79 plus 121, that's a mass of 200. So they go and put that mass right here. So this is the mass number right here. And then this is the proton number right there. So you get the mass number on top, proton number on the bottom, and the symbol. And if there was a charge, they could put it there. So maybe this has 80 electrons as well. So number of protons, 79 minus 80 electrons. That comes out to -1. So we also have a -1. So all the charge information about your atom is there. All the mass information about your atom is there. What type of element is there? Because you have both the symbol and the mass atomic number. So both of these, atomic number, this will tell you how many protons you have and what element you have, and the atomic symbol. So you got two ways of knowing which element you're working with there, both the atomic number and the atomic symbol. Both tell you that this is gold, because gold will always have 79 protons no matter what. And we'll give you a periodic table, so you don't need to worry about memorizing the atomic numbers, because we can always look those up there. But this is a lot easier than saying, you know, gold with 79 protons, 121 neutrons, 80 electrons. We can get all that information in a very small kind of compact way. So this is a way of kind of giving that information out all in one kind of go. So for like the helium one, right, we were using this example before, right? We want to write this out. What we have, and helium's got 2 protons, so its atomic number is 2. So that's the number that's going to go down in this corner here. So we have a 2. And then we need to put a mass up. So you have protons down here, protons plus neutrons, the symbol, and then protons minus electrons. So as long as you know protons, right, 3 of these numbers all require protons in some way or another, right? The mass is the protons and the neutrons added. The electrons minus the protons, that's the charge. So charge needs protons, mass needs protons, atomic number needs protons. So the proton number is pretty important there. And it's going to come up kind of 3 different ways. So kind of filling out our thing, we know the symbol for helium's He because they told us, but we could always look that up on our space up there. So, right, we put our big He. We also know the atomic number right away was 2. And then the mass is the number of protons plus the number of neutrons. So 2 plus 2. So our mass we'll put up in this top left corner, 4. And then the other thing they wanted to ask about was charge. Charge is just the number of protons minus number of electrons here. So that's 0. So this doesn't have a charge. So that's okay. But that's a way you could talk about helium. It's got 4/2 He. That's a way of kind of describing a helium atom that has 2 protons and 2 neutrons. Or if we wanted to do the same thing for like this iron right here, right? This iron atom, we're going to do the same thing. The number of protons, so the symbol for iron is Fe. So we can put that down here. And we know that it has 26 protons. We'd get that from looking up the periodic table, or maybe they just tell us. So we'll put that 26 down here, 26. And then we need the mass again. So mass is protons plus neutrons. So in that case, protons is 26. We'll add the number of neutrons, which is 30. Yep, so 56, yep. And then we need proton, and then our charge, right, is 26 minus 25. So we got a +1 for that one. So, right, so we got our atom there. So this is our way of writing out an iron for this particular one. So if we wanted to talk about this particular ion and not iron and not write out all this, all these numbers, we could do that. So this is kind of a way. But other irons may exist as well that have like a mass of 55 or have a mass of maybe 60. But they're always going to have this part down here the same. right? They're always going to be irons with an atomic number of 26. So because iron always has 26 protons, but the mass may change a little bit. This iron's a little bit heavier. This iron's a little bit lighter than the other one because they have different numbers of neutrons. So you can kind of change the number of neutrons, and that may change your atom's mass. But as long as you have the same number of protons, the atom stays the same in terms of what atom it is. It's not going to turn into a different kind of element. It's still going to be the iron there. And that's what these things called isotopes are. So isotopes are when you have different elements that are a single element that has a different mass. So an iron with 56 versus an iron with 60 versus an iron with 80. The mass of the iron is just how many protons and neutrons there are, and you can have different numbers of neutrons. So you can see these lithiums right here all have 3 protons. I don't know why they're... So all these lithiums have 3 protons, but they have different numbers of neutrons. One only has 3, one has 4, one has 5. So we got different masses. 3, 4, 5. So this one's got a mass of 6, 7, and then the other one's 8. So the masses of those lithiums are going to be different a little bit from each other, but they all still have the same number of protons. So they're all still lithium atoms there. And that's important because it means that they behave the same in terms of their chemical reactions. So just like if you look at your phone, inside your phone is lithium batteries, and the lithiums may weigh 6, they may weigh 7, they may weigh 8, but they'll all behave the same way. They're all going to power your phone the same way. It's just some are a little bit heavier, some are a little bit lighter. If you look at coins or money, right, there's different years on it. So all the pennies in this pile have a different year, but they're all worth a cent. Or all the dollar bills or the $10 bills or all have different serial numbers or different print years, but they're all worth the same amount for those. Atoms will have different masses, but they still behave the same. So these lithiums are all going to behave the same except for whether or not they're radioactive or not, but they'll have the same kind of chemistry for those. It's just that the masses may be a little different because it turns out that most atoms, they don't always have the same number of neutrons. So even for the lithium here, you'll get an average. Some lithiums have 3, some lithiums have 4, some lithiums have 5, but they'll all behave the same way in terms of their lithium abilities. It's just some are heavier than others and lighter than others. And that means when you go to weigh out the lithiums, you have to be kind of careful with the weights, because if you're trying to figure out how many lithium atoms you have, if you have the lighter or the heavier mixture, you may get the wrong number of atoms because of the way the weights work out. So what we do is for atoms, if we want to know, because there are all these different types of lithium masses, we got to have kind of an average, right? Because sometimes you have lithiums that weigh this much, sometimes you have lithiums that weigh this much. So we use the average mass for most of these atoms. So we use an average of all these different masses, depending on, because maybe this one's really abundant and there's about 80% of this one, and then the other one's only 5 and 15%. So most of the time you see this particular version. So we use an average mass to kind of correlate the differences between these, so that you kind of get an idea of how many lithiums you have if you were to weigh it and see how many lithiums you have in that pile of reactions. So just to kind of summarize the difference, right? We got kind of different words. We have isotopes, we have elements. So elements are different, like this. These are 2 different or 3 different elements. These 3 elements all have different atomic numbers. So you have the element of hydrogen with its atomic number of 1 or its proton number of 1. You have this element over here, which is a carbon with a proton number of 6. So these are all different kinds of elements. They have different atomic numbers. But you can also have things with the same atomic number, but different masses. And those are things that are the isotopes. So isotopes have the same atomic number, right? They both have 6, but their masses are a little bit different. So in this case here, one carbon weighs 13 and one carbon weighs 14. So when we're talking about the isotopes, we're talking about elements that have the same atomic number, but different atomic masses. So they're going to have the same number of protons, but their masses are going to be a little bit different for those. So that's when we're talking about isotopes and elements. That's what we're referring to. They're referring to the numbers of if we're referring to elements, we're looking at, do they have the same number of protons or not? So if you have the same number of protons, you are the same element. If you have different number of protons, then you're different elements, right? Hydrogen and helium, those are two different elements because hydrogen's got one proton, helium's got two, versus these have the same number of protons. They are the same element, they're carbon, but they've got different masses. And elements with the same mass or different mass are isotopes. So this is an isotope of carbon, carbon-13. And then this is an isotope of carbon, carbon-14. So two different carbon isotopes, a couple of different kinds of elements there. And when we talk about radioactive elements, we're going to be talking about the isotopes of that are radioactive, meaning because some carbons are not radioactive and some carbons are. And that's the isotope effect for those there. So the mass is going to kind of change depending on what the elements are. And if you want to figure out for atoms, like if we were to look at the periodic table, we can get the atomic number pretty easily. There's an atomic number for atoms up here on these numbers, but there's other bits on the atomic table, periodic table too. There's also, right, so this is our number of protons. And then on the atomic number, there's also another number down here. But it's not a whole number usually. It's a number with a lot of decimal places. And this is a mass for atomic. These are the atomic mass of an element. But it's not a standard number. It's not an integer number. It's a number with kind of decimal places. Because again, when we go back to kind of elements in nature, they exist in multiple forms. They exist as different isotopes. And what they've done is they've looked at all the different elements, isotopes of that particular element, and they've weighed them out. They've weighed out the mass, and they've figured out that the mass has a number there that's equal. So you can kind of see, for instance, in lithium, there are two different types of lithiums. There's lithiums with a mass of 6, lithiums with a mass of 7, that both exist in nature. But it turns out that only 8% of the lithiums you'll ever see. So only 8% of the lithiums in your phone are in this lithium-6 conformation. The other 93% of the lithiums in your phone are lithiums with a mass of 7. And therefore, if you were to kind of take 1,000 lithiums or 1,000,000 lithiums and kind of get an average of the mass, 7% would have a mass of 6, 93 would have a mass of 7, and the overall mass of the lithium, the average mass of the lithium would be 6.9, because 90% have a mass of over 7. The other 7% have a mass of lower. So you can kind of get an idea of how many lithiums there are. So for when you want to look at an atom and say, all right, well, this number, it's somewhere between 6 and 7, and it's at 6.9. So it's pretty close to 7 and really, really, really far away from 6. So if you were to look at an atom, the average masses of these, it kind of tells you what are you more likely to see. Are you more likely to see something with a mass of 6 or a mass of 7? Well, if the average mass is really close to 7, then you're more likely to see the one with a mass of 7 on a random basis. And it turns out that 93% of the time, that's what you're going to see. So if you had just a bag of lithiums and you were to reach in and pull out one at random, 93% of the time, you're going to pull out one that has a mass of 7. That's the kind of the average mass you'd expect to see. So if we're trying to figure out like which mass do we see more often, look at the average mass, which is the bottom there, and see is your number closer to which number you're closer to. So do you round up or round down? 6.9, you'd round to 7 because it's pretty close to 7, versus if you had like 6.1, you would probably round down to 6. So there's a couple of homework questions that ask like what mass you're more likely to encounter. And that's what they're asking you to do, is kind of look at the atomic table and say, all right, is this number close to, what whole number am I closest to right here? Am I close to 6? Am I close to 7? Am I close to 12? For those. So this is kind of showing the same thing for carbon, right? So carbon on the periodic table, it has an atomic number of 6, so it's got 6 protons, and it's got an average atomic mass of 12.01. And that comes from the fact that 99% of the carbons that exist have a mass of 12. That means they have 6 protons and 6 neutrons. Versus the other 1% are 6 carbons, protons, plus 7 neutrons. So this is going to be 12. This one's going to be 13. Got 2 masses there for those. So those are the 2 masses for the things. And then, but that means like, so if you had a bunch of carbons, what are we closer to? Are we closer to the 12? Or are we close to the 13, right? We're really, really, really close to 12. So compared to those, carbon 12 is more abundant than 13 because that mass is much, much, much closer to the 12 than the 13. Same thing for this boron here. We could do the same thing, right? Are we closer to 10 or are we closer to 11, right? We're closer to 11. 10.8 is closer to 11 than 10. So boron 11 is more abundant or more likely to be encountered than the 10 version, again, because the mass is closer to the 11 there. So there's a couple questions that talk about, what mass do you think you'll see more often? Just look and see what mass is closer to the average. Is 12 or 11 or 10 or 13 closer to 12? 12 is the closest to 12 for there. So this was just kind of a version of this. So for the different types of homework questions, when you're looking at these, well, that's fun. There's no image to click on. Well, there would have been a spot to click, so we'll skip that. Don't know why that didn't work. So for these atoms, though, the reason why those masses are important is because some atoms or some isotopes are stable and some isotopes aren't. And the isotopes that are stable are fine. You'll never have to worry about them. But the ones that aren't stable, they'll break up. So just like if you have too many protons in a nucleus, there's too much positive energy there, and they're all trying to get away from each other. There's not enough neutrons. Eventually, what will happen is one of those atoms, one of those particles will leave the nucleus, and that causes the nucleus to break a little bit, and part of it goes away. And that gives off a lot of energy, and that energy has to go somewhere, and it goes into that particle that then shoots out and then can damage other particles or damage other things. So not all nuclei are stable, not all isotopes are stable, and the unstable isotopes, they're molecules that are going to break apart. They're going to be radioactive. And radioactive stuff is useful for us because we use this in medicine, right? We use radioactive compounds in medicine. We use this for if you have any kind of cancer therapy, you need to kill a cell, or if you need to do inoperable, you don't want to cut into somebody's brain really deep in the brain, but you might want to adjust the brain so that you can get kind of into the cell area there. So you're trying to get into an area that you can't cut apart. But you can use radiation as a beam of radiation, almost like a laser or a knife, to kind of cut into the person and do operations in areas that you normally couldn't get to with surgical tools. You can use this as ways to look for cancers that are undetectable by other methods. So it's hard to detect certain cancers using biopsies or using screens, but you can use radioactive materials to look for those cancers. And even sometimes you can use those radioactive materials to treat cancers and remove those tumors. Industrial processes, sterilizing food, keeping your house safe from smoke, lots of really important uses of radioactive materials or isotopes that happen to be slightly unstable for them. So there's lots of radioactive isotopes, it turns out. It turns out there's only a very small number of atoms that are stable, and that's this kind of line in the middle here. And we had been talking about earlier the number of protons versus the number of neutrons. And this is kind of a line here, number of protons versus number of neutrons. And if you look at the ratio, it kind of changes over time. So it starts off as kind of a 1-to-1, and then it goes more of a 1-to-2. So it kind of does this shape there. But depending on how many protons and neutrons you have, your elements will change shape and structures there. Oh yeah, the question didn't show up for some reason, so we skipped. It didn't have a picture there. Um, so when we talk about things that are radioactive, there's kind of three different types of radioactive particles that can come off from those molecules. So you have radioactive particles that give off things called alphas, or it looks like a little fish for its symbol. And then the other two are betas, which look like a bee with a tail for them. And they can either be betas or gamma positrons. And then gammas are another type of radiation, but it's not a particle. So kind of different ways of giving off part of your nucleus. You actually break off part of your nucleus, and you either break off part of your nucleus as an alpha or a beta or a positron, but it's actually part of the nucleus that's getting shot out at really, really, really fast speeds. And that can cause the element to kind of lose some of its energy and finally become enough stable that it stops reacting. So what we're talking about with nuclear reactions is what we're talking about are reactions that actually change one element into another. So you go from something like gold to something like platinum, or you have mercury turning into lead. You actually, with radioactive elements, radioactive equations, and radioactive decay, you actually change the element from one type of element into another because you're changing the number of protons. So if you change the number of protons, you can actually cause an element to change from one type to the other. Normally, elements don't go changing from one element into the other, but with radioactive processes, they do. So you can change elements from one type to another using a radioactive decay. So you can see, for example, with this element reaction right here, we started off with the uranium element. It had 92 protons, and it had the symbol of U, so uranium. And then what we did is we had a radioactive process occur. That uranium wasn't stable for some reason. So this uranium isn't stable, and it breaks down, and it went from being uranium to being some other element to being thorium because the atomic number changed. And when this element broke, it actually kind of it was a big element, and then part of it broke off and got kicked off. And now you have this new element that's missing a piece. So that element is missing a few protons, it's missing a few neutrons, but that's what it needed to go from an unstable radioactive element to a stable non-radioactive element. So this element is missing a little bit of its nucleus, but that was just enough to kind of make it stable again. So certain nucleuses just aren't very stable. One of them that's not stable is uranium, and it breaks off part of its nucleus and shoots that out and makes the element now a more stable type of element particle there. Or this other element right here, this oxygen, didn't happen to be very stable. It has a lot of neutrons, not so many protons. So right, this has 11 neutrons, 8 protons. And what happens is this element also gives off a particle, and that makes it change into an element that now has 10 neutrons and 9 protons. And now the number of protons has changed in both of these. And when you change protons, you change elements. When you change elements, you go from one type of element to another. You go from being uranium to thorium, or you're going from being oxygen to fluorine. But either way, you're changing elements. You're changing from one type of element to another. You're changing what element you have there. But you're also going from something that's radioactive or unstable to something that's stable, which means it's not going to decay any further there. So these elements are trying to get stable again. They're trying to get to a point where they're not going to be breaking down or reacting. And that's what they do by kind of changing their atomic numbers, by either turning an electron into a proton or protons into neutrons, or breaking off part of their things and giving off these particles. Then they're causing the element to change into a new element that's stable again. So nuclear reactions are actually changing elements. They're changing from one type of element into another. They're changing your proton numbers from one to another. So you can see kind of here, you're starting with one product, turning into something else. But another thing that's interesting about protons is the total numbers of particles is the same. If you count the number of masses, if you count the number of atomic numbers and masses on the left versus on the right, you'll see that it doesn't change, right? So you started off with something with a mass of 235. We started with something with an atomic number of 92. And if we look at all the atomic numbers on the left and all the atomic numbers on the right, we'll see that they don't change. If we look at all the masses on the left, all the masses on the right, we'll see they don't change. So we started with atomic number 92 right here, and then we ended with a 90 and a 2. So even though we switched the elements around, even though we moved things around, even though the elements moved from one type to another, you started with 92 and you ended with 92. It's just you started with 92 and you ended with 90 and 2, but they're all still there. And the same thing for the mass. The total number of protons and neutrons doesn't change. Started with 235 and we ended with 4 plus 231. So we still end with 235. We've just rearranged things a little bit. And you see that on the other side as 2. We started at 19 on top, and we end at 19 by having 0 and 19. Or over here, we started at 8, and we end at 8, but we end at 8 by having either 8 or -1 and 9. But right, 9 minus 1 is still 8. So we're still going to have these masses and these atomic numbers adding up the same, but they're going to add up the same in different ways. So rather than having 8, we have 1 and -9 and 1 versus 8. Or having 19, we still have 19. So these are kind of the particles. So whenever you're looking at a radioactive equation, you always want to make sure that your atoms and your numbers add together. So double check that your masses on the left and your masses on the right are the same. So double check that these all sum together. Double check that your atomic numbers all sum together as well. So you're always going to be making sure that atoms come together or atoms come apart, that the masses are the same for those. So we'll talk about the different types of radioactive decay today. We'll just kind of talk about maybe 1 or 2 of them before run out of time. But these are all ways of just stabilizing nucleuses. We're trying to make our nucleus stable. We're trying to make our nucleus have the same properties of a stable nucleus. The number of atoms and electrons and protons and neutrons all together are a way that the atom is comfortable and happy and not giving off random particles and energies. And one of the ways that really, really big atoms do this is that the atom's just too big. There's too many neutrons and too many protons. Not enough protons or neutrons, too many protons. And what the atom does is it just kind of it breaks off a piece. So just like if you took a big rock and you hit it with a hammer and a piece of the rock flew off, that's what's happening with our alpha emissions here. You can see a little cartoon of this atom right here, and it lost part of its head. So it lost these little pieces right here, and the mass is still the same. If we were to weigh the mass over here and then weigh the mass over here, it's the same because part of it is broken off. And just like if you took that big rock, you smash it, and then you made sure to pick up all the pieces, it's going to weigh the same. It's just now a pile of rocks instead of one big rock. And the same thing happened over here. We weigh the same as we did before. It's just part of it's broken off. And you can see, right, he's missing something. He lost part of his head. So part of it broke off right there. And this one flies away. And that makes the overall mass the same, but the mass of this particular part is lower. It lost some protons, it lost some neutrons, and that makes that element a little bit more stable. So you can see right here, right, the mass of this element was 235. The mass is going to drop down to 231, but those other 4 aren't lost. Those 4 got kicked off as a new particle. And we can either write that as a 4/2 alpha or 4/HE, depending on which kind of book you read. But this is the same particle. It's just a particle with a mass of 4, and of that mass of 4, 2 of those element components were from protons, and 2 of those were neutrons. So this gave off 2 protons and 2 neutrons, right? Mass is neutrons plus protons, so mass of 4, atomic number of 2. So the atomic number goes down by 2. The atomic mass goes down by 4, and that makes the element a little bit more stable. It goes from something with a mass of 235 down to a mass of 231. An atomic number 92 atomic number goes down to 90. And that may be enough to make this element stable again, so it doesn't have any other reactions going on there. And that makes it a stable nucleus, ends the radioactive decay. So that's one way that really, really big atoms especially, so you'll see this for things like uranium, anything with a mass above 100, anything with an atomic number above about 40, those are going to be giving off these alpha particles. This is what's called alpha decay or alpha emission, because it gives off something that we call an alpha particle, but an alpha particle is very similar to a helium atom. So if you want to know where does all the helium on Earth come from, most of the helium that we have, the helium we use in balloons, helium we use in other kind of industrial applications, that all comes from radioactive decay. So things like argon and radon and other atoms, uranium, they're all deep in the Earth. And over the years, they've been doing this alpha decay, this alpha emission type process. And as they give off these helium atoms, those helium atoms got stuck in the rock around them. So you had a bunch of uranium, it starts breaking down into thorium and giving off heliums. You have a bunch of radon, it starts breaking down into polonium and lead, and it gives off heliums. And all that helium got trapped in the rocks. And you can drill down, so helium actually we get from wells. So you get helium from wells, just like how you would get oil from wells or water from a well. We can get helium from a well as well, also. So you have these little pockets of gas, just like natural gas can be drilled from wells. So you drill a well, and then you get all the helium out. And then you have that helium that you can use for all sorts of different things. We use it for balloons, we use it for other magnets and applications, but we also use helium for medical stuff. If you ever had an MRI done, the magnets that work with an MRI are cooled by liquid helium, or if you needed something really, really cold, helium is used for that, or a gas that's safe to breathe but not oxygen, we'll use helium for those. So it has really important applications, and actually every time helium gets out into the air, it eventually floats away into space. Helium weighs so little that it can just leave Earth, and it can just float away into space forever. So helium's kind of one of those non-renewable resources, just like the same anything that we burn, you can't turn it back into the gas. Helium can float away, but we use it for lots of neat stuff. But helium comes from radioactive decay. So helium is the product of years and millennia of radioactive processes going on underground and getting trapped there and getting trapped in the rocks. So we'll do just one or two more types of particle experiment discussions here. So we talked about one, right? We talked about alphas, and that's one way of changing an element from one type to another. And then the other two types of reactions that we can talk about are betas. So betas are another way of changing an element, and they're a little different. They're changing neutrons and protons into each other. So rather, and they're these particles that basically cause an element to change types. So betas look like a little B, like there, and they usually have a little minus after them too. So you got to make sure, because there's both betas and positrons. So make sure that you use the right ones. This is the beta one. We're not going to be using that one yet. So this is the symbol for it. And what happens with a beta is, right, so you have electrons and you have neutrons and you have protons. You have all those different particles hanging out in an atom. And the nucleus is made of both protons and neutrons. And what happens is a proton has a mass of 1, right? So protons have a +1 charge and mass of 1. And the neutrons have a mass of 1 and a neutral charge. And you can kind of think of them having basically a plus and a minus together, because that comes out to the same as no charge. So if you think about a proton as having kind of a neutron, a neutron is basically a proton plus an electron. So together. So if you had a proton and an electron together, they would have a mass of 1 and they would have no charge, because the plus from the proton and the minus from the electron would be the same. And what happens is with these atoms is the neutron splits up. The neutron is normally not going to change, but that neutron goes from being a neutron to turning into a beta plus a proton. So neutrons have no mass or no charge. This now has a +1 charge, but this has a -1 come on. And this has a +1. So your overall charge doesn't change. -1 + 1 = 0. So you start at 0, you end at 0. You're taking that beta, you're releasing it from the nucleus, and you're turning a neutron into a proton. So if we look at our atom right here, it has a certain number of protons and a certain number of neutrons, and we're taking one of these protons or neutrons, and we're turning it into a proton. And that's going to change the atomic number. So you have an atom here that normally, so like this oxygen right here, oxygen has 11 protons, or 8 protons, and 9 neutrons. So, right, so this is our starting atom. Our starting atom has 8 protons, 11 neutrons, and then what happens is a beta particle gets kicked out of that nucleus. And that beta turns one of these neutrons here into a proton. So now we have only 10 neutrons. And one of these neutrons turns into a proton. So that means 8 + 1 is going to become 9. So we went from having 11 protons and 11 neutrons and 8 protons to having 10 neutrons and 8 protons. So our numbers changed. We went from 8 to 9, and we went from 11 to 10. But if we look at the total number of particles that are there, then we have the same number, right? We still have 11 + 8, that sums to 19. And then 10 + 9 also sums to 19. So the overall mass doesn't change, right? You started at 19, you end at 19. The overall mass doesn't change, but the ratio of protons to neutrons does, because we're actually turning a neutron into a proton during this process. So beta emission, you turn a neutron into a proton. And that means that your atomic number goes up, right? Because if the number of protons goes up, the atomic number goes up. So if you had oxygen, which has atomic number 8, and you turn into something with an atomic number of 9 by gaining a proton, you turn an oxygen atom into a fluorine atom, or you could turn a carbon atom into, you could turn a carbon atom into a nitrogen atom. What's going on? That's weird. There we go. So there we go. So you're starting with these atoms. So right, you're changing atoms from one type to another. So you're going from protons to neutrons. These atoms are changing from one type to another. So you're changing from one type of atom to another. You're changing your proton number there. So you're increasing your atomic number. You're increasing your number of protons. So number of protons goes up. Number of neutrons goes down. But your overall number of protons and neutrons together stays the same, because if one goes up by 1, the other goes down by 1, it's an overall same number for those. So this is what's happening with these beta reactions. Betas are when we're kicking off, turning a neutron into a proton, so our proton numbers are going up, and we're changing elements from one type to the other. So that's a reaction that can occur to make the kind of nucleus more stable. But in the process, you also kick off this little particle. So this particle goes out and causes damage in terms of radioactive elements. This is coming out of the nucleus and going off into the environment. But the element itself is becoming more stable in the process. So you can do beta emission, which is where we're turning a neutron into a proton, making our atomic number go up. And then the other one, so we just did that. So just to kind of show this again, right? So our atomic number goes up for beta, and our mass stays the same. So when you look at the beta reactions, you can check the masses. You see that, right? The mass started at 19 and it ended at 19. So if you see a nuclear reaction where the atomic number goes up but the mass stays the same, that's a good sign that we have what looks like a beta. So you can kind of compare the alpha versus the beta. A couple different symbols are used, a couple different masses are changed as well. So for alphas, right, we see the symbol of an alpha, it looks like a little fish, versus the beta is a bee looking symbol there. So two different ways. The other thing to remember is that betas also have this minus. So you got to remember that there is a minus there when you're talking about betas. So if you see a minus sign after it, that's a good sign you have betas. So different symbols for these. But they also, the particle that gets kicked off is different. So the particle for alpha has a mass of 4. The particle for a beta doesn't have a mass. It has no mass. The particle for an alpha has a +2 charge. The particle for betas that get kicked off have a -1 charge. So these different particles have different symbols, they have different charges, they have different masses. And what alphas do is alphas cause the atomic number to go down by 2 and the mass to go down by 4. Versus the betas, the atomic number goes up. So if you see atomic number go down, or if you see mass, so number of protons, if we see that go down, if we see the mass go down, that's a sign we have alpha. If we see the mass stay the same, we have beta. If we see the mass go up, if we see the atomic number or the number of protons go up, then we have beta. So look and see, right? Does the mass go up or down? If the mass goes down, you have alpha. If the mass stays the same, you have beta. If the atomic number goes down, you have alpha. If the atomic number goes up, you have beta. So you kind of look and see, right, what's going on with these reactions. Do we see a mass up or down? Do we see atomic numbers up or down? What kind of particle do we have that's coming off of it? So those are two of the types of particles, and we'll wrap up with kind of one more. So we have both betas and positrons, and both of these have the little B symbol, but the thing to remember for betas, it's B minus, and positron is B plus. So now we're on positron, positron's B plus. So you want to check, make sure if you see that little B, is it a B plus or a B minus? B plus is the positron, and those are things that have a +1 charge. So betas have a -1, positrons have a +1, and both betas and positrons, they won't change the mass. The mass stays the same throughout. So you see the mass started at 18 and it ended at 18. And a positron's kind of like a reverse beta. It leaves the mass the same, but it makes the atomic number go down. You start with 9 protons, you end with 8 protons. So we have two different things that can lower the atomic number. Both the atomic number can go down from alphas, and atomic number can go down from positrons. So we'll see the mass go down, but not change for atomic numbers. So comparing those two, we want to make sure we have the right one. We don't want to get confused, right? So betas have a B with a minus, positrons have B with a plus. So looking at the difference, right, that's one difference in the symbols right there. One is plus, one is minus. The actual types of reactions that occur too. In both cases, the mass stays the same on both sides. If you start with a mass of 18, you're going to end with a mass of 18, right? 0 plus 18 versus 18 for both of these. Right, so mass doesn't change, but what happens is atomic numbers do. So atomic numbers change in both cases, but for betas, the atomic number goes up. So right, you start with an atomic number of 7 protons, and you increase to 8. So in this case, you started with nitrogen. So we had a nitrogen over here, and our nitrogen had 7 protons and 11 neutrons for a total mass of 18. And what happened is we turned one of those neutrons into a proton. So we ended with oxygen with 8 protons and 10 neutrons. So our number of neutrons went down by 1. Our number of protons went up. That means our atomic number went up. So P goes up and neutrons go down. So neutron goes down, proton goes up, atomic number increases, but the mass stays the same because the total number of particles didn't change. It started with 7 and 11, you ended with 8 and 10. Both of those still add up to 18. So the mass is still the same. Mass stayed 18 for both. But down here, we had the positrons. This is kind of similar reaction, except now we started with this guy here, which was 7 protons, 11 neutrons, so same starting material. And then we ended with something with only 6 protons and 12 neutrons. So you can see here right now, the proton number has gone down, neutron number has gone up. And the total mass is the same. 7 plus 11 is 18. 6 plus 12 is also 18. So the mass doesn't change in these cases. So both for beta and positron, mass stays the same. But for beta, the mass stays the same when the atomic number goes up, or the number of proton goes up, right? Start with 7 protons, end with 8 protons. Versus for positrons, the number of protons started at 7 and it went down to 6. So proton number goes down in positron, proton number goes up in beta. So those are the two differences there. So proton number goes down, beta or goes up in beta. So betas have this B minus symbol. Proton number goes down in positrons, they have this little B plus. So two different types of reactions that can both change the atomic number, but leave the mass the same for those. And those are both two different types of radioactive decays that can cause that to happen. So we got kind of two different ones. One has a -1 charge, one has a +1 charge. One makes the atomic number go up, one makes the atomic number go down. But in both cases, the mass doesn't change. So unlike alphas, the mass goes down. So I'll just write down quick here. Atomic number protons goes down by 2. And then mass goes down by 4. So with alpha particles, the atomic number goes down, similar to positron, but it goes down by 2. Also, though, alphas, it goes down in terms of mass. But positrons don't change the mass, betas don't change the mass. So the only time you're going to see mass go down is with alpha. So kind of for that. So if you ever see a mass decrease, that means you're giving off alphas. But if you see the masses stay the same, it's either one of these two. And then you have to look, well, my mass stayed the same, but did my atomic number go up or down? And depending on if atomic number went up or down, you'll have one of these two types of reactions going on there. So that's a good spot to stop today, I think. So that's a good spot.